Let's find the analytical solution to this following parachutist problem. And as an example, we will assume that the body of the person is 68.1 kilogram and it jumps out of the stationary hot air balloon, and we want to calculate the velocity prior to opening the chute, and the drag coefficient is 12.5 kilogram per second. And for this we are going to use the analytical formulation that we defined in the previous slide. Let's write it again with the parameters here. So we said that T is equivalent to M times G. It was M is 68.1 and G is 9.81 divided by the drag coefficient C, 12.5 kilogram per second, and there was the parenthesis term 1 minus the exponential and minus C over M, which means 12.5 minus, over 68.1, and this is multiplied by T. So T is not now, that's why we keep it as T. And if we make the multiplications over here, it becomes 53.44 and 1 minus e to the power minus 0.18355 t. And this is the mathematical formulation to find the velocity. And let's try to calculate the time by starting from t up to 12. So if we say t is 0, then v0 is equivalent to simply 53.44 1 minus e to the power minus 0.18355. So simply what we do is we just substitute the t values to the equation and find the results. Here v is 0. Then we use t equals 2 and we substitute t values in the equation. The result is v2 16.42 meter per second, and we will go from 0 to 12 by increasing t with the interval of 2, and here's 0, 2 and 4. v4 is 27.8 meter per second. If t is 6, v6 is 35.68 meter per second. If t is 8, v8 is 41.14. You can simply substitute the t values to the equation and calculate using your calculation. This is meter per second again. T equals 10. v10 is 47.54 meter per second, and finally t equals 12. v12 this is 44. This is 44.92. This is 47.54 meter per second. We can continue up to the infinity here, and for infinity we will have a constant velocity after a while, and it is actually 53.44, and you can see that we reach to this value with the increments of t. And if we want to have by the way, this the velocity at infinity, which is constant, is called the terminal velocity, and the parachutist, while falling down, will reach this final velocity eventually. Then it is actually the time to maybe open the parachute, let's say. So if we try to draw the velocity curve over here from 0 to 12, this is t in seconds, and the y-axis is v in meter per seconds, and it goes up to 53. So let's say this top part is the constant velocity, terminal velocity, 53.44, and let's define it as constant like this. This is just the velocity that we reach eventually, and if we draw these values to here, starting from 0, t2, t4, let's draw them as well. Here for 0, it's 0 anyway. Here for the 2, the value is 16. Let's divide this as, this is 50, maybe 40, 20, 10, 20, 40, and here 2, 4, 6. This is, we can change 12. Ten, 12. Let's make this way. And for 2, the value is 1642, somewhere here. So we can have the first value. For time is 4:27.8, somewhere here maybe, or actually it's too much. It's below 30. So somewhere here, let's say. For 6, 35. You can say this value. For 8, 41. Somewhere here. For 10, 44. Sorry, for 10, 44. Here, and finally for 12, 47. This was 50, so 47 is here. You can see when we increase the time, the velocity is getting closer to each other and making a horizontal curve, kind of. Let me try to draw this, if I can. If we combine these, we can see that it's going up to the constant value with a parabolic curve, as you can see. So eventually it will reach to 53.44 when we increase the time. This way we can see the trend or the behavior of the velocity of this parachutist example.